TDM, and now you connecting another input output to the CRO. Okay, so what you're going to set means you're going to set the input function. So the first level is nothing but VPP of 1.98 is there. So if you want to change, you can change it, no problem. So this is your amplitude variation. So if you change the amplitude variation, it will change. So I am setting for 2 alone. So it is exactly 2 volts. I am setting a frequency of 1 kilohertz. So I am linking through the TDM. So the TDM acts as the intermediator here. Okay. So here the source generator, here the TDM, and your the DSO is there. So if you press auto set, so you're getting the signal. Okay, it has been dispersed. You will get like impulse signal. It has been damping. So like this. So we'll get the signal like this. So that is your input. Okay. So normally how we set the input? So perfect sine wave or perfect square wave. So here you will get the signal in this way. So if you see there, so what is your VPP means? It has been dispersed of 760 millivolt only you are getting. So here we set 2 VPP, but here we getting the 7 millivolt. Okay, so please note this thing. Actually, I am asking after completion of this experiment. So what are the bottlenecks? And the frequency we have set is 1 kilohertz. Okay. So now, what is the objective of this experiment? Actually, our objective is that to calculate the system bandwidth. So for that, I am going to do. So since I have connect from FG to IO2, okay, input output 2, and take input output 2 to P11. So P11 is your analog input. Okay, since I have connected the input output 2 to the function generator. Okay, so I am connecting at input output 2 to analog input. So in analog input, so before entering into this buffer, okay, driver, so it should be an electrical thing. So once it get into this loop, okay, this is nothing but a PLL. It will be working like a PLL logic. Okay, so it will convert into the optical, either in the transmitter 1 or transmitter 2. In transmitter 1, it a signal comes in IR form. Here it will come in LED form. Okay, so now what you going to do means you have to connect the another thing, input output 1 to P31. Okay, P31 is your receiver. Okay, so which is in between to the driver and the comparator. So comparator which does the logical comparing of the two variables. Okay, so this is the driver unit. Okay, so if your gain factor is very less, then you can adjust this knob. Okay, so now I am going to insert the optical fiber of 850 nanometer. That means you will get a IRS that has been connected to the optical receiver. The optical receiver. So here no need to check the transmitter output, these things. You're going to see the output here only. Okay, so by varying the frequency, okay, so you're going to check the VPP value of here. Okay, so you have set to 2 volt anyway, so we cannot expect the same 2 volt will come in the output in the TDM. Okay, but you will get some output voltage come for varying the each frequency. So I have set 1 kilohertz. Okay, so you're going to observe the frequency here, and you're going to check the output voltage VPP there. So once you keep on varying, okay, so for example, and so now at 1.14 kilohertz, so it will be dispersed only, so don't bother about this signal. So now again it came to 2 volts. So previously how much? Some 750 millivolt. Okay, so you can keep on raising the frequency and check the, press auto set and check the VPP, gradually increase somewhat, not suddenly increase, somewhat gradual increase will be there. So you have to keep on varying the frequency up to some certain band. Okay, so whatever it may be, it may goes to some 10 kilohertz, or it may be anywhere. So here also it's sustain and this some 2 only. So at one level it will come down. So that point, once we do several iterations only, we can know. So here also the 2. I am moving to the megahertz range. Just keep on rising. Actually it is fluctuating, it is coming some 1 point something also. Okay, 1 point something, it rise to some 3.3 volt. So now it's coming to 1 point also. Okay, it is fluctuating. So what, so while you observing the reading, you have to unstop it and take the reading. So which means that the pattern going like this, the frequency response gradually increase, maintain some range, and it will decrease. Okay, so after that you have to plot the 3 dB, sorry, you have to draw the 3 dB line. From that you have to find the 3 dB bandwidth. Okay, so this is the 3 dB bandwidth calculation by using the TDM kit. Okay, so you have observed this experimentation. So from this I want what is the inference and what are the bottlenecks of the TDM. Yeah, dispersion. One thing is that dispersion. The next one is the gain is somewhat poor. Next, delay will be more. Next thing, even then I am synchronized. Okay, so even then I am synchronizing So if you see the previous experiment, even then synchronizing with marker generator and marker reference, you're having a delay. So there is synchronization is also not be a good one. Okay. So these are already the issues available in the TDM. So what only in we are moving to the FDM. Okay, frequency division multiplexing. So, but in our laboratory we are not having FDM, but these bottlenecks has been removed. Okay, in that case, delay. So, but through this we can calculate the numerical aperture. So there are several factors are there, like to improve our quality of service. So we have to measure the optical parameters first. Through these are the one of the parameter. For that you having a device. So through we can optimize our loss factors. Okay, so we can rectify to produce the good fabrication of the optical material. Okay, so do you understand this thing? So this is one of the technology used in the first generation material. Okay, so we next thing I will show you the setup alone. Okay, so next week I will show you the demonstration of the experiment. Okay, so please move to there. We will check that block also. So whatever we have seen in class, that we will see there. So move there. First one.